Hello, welcome to this optimization video. We got 6 problems here. We'll try to get through all of them. Make sure to pause or slow down the video if there's anything you need to think about or if anything's confusing. I'll try to explain as much as I can, but I also don't want to use too much of the time here. So let's see what we can do. This is an old homework that I used to give to AB students. I think I'm just going to use this for practice for you guys. So no, this is not homework. Scratch it out. Not homework. I want you guys to enjoy your Thanksgiving break. I'm not assigning anything over the break, but I do want y'all to get this practice in while we're in class. So anyway, question 1. A cryptography expert is deciphering a computer code. To do this, the expert needs to minimize the product of a positive rational number and a negative rational number. Given that the positive number is exactly 7 greater than the negative number, what final product is the expert looking for? Okay, interesting. So what are we trying to minimize or maximize? We're trying to minimize the product of these two numbers, right? This is where our primary is going to come from. And then what is our secondary? What is the thing that's limiting our possibilities here? It's the fact that the positive number is exactly 7 greater than the negative number, right? This is our secondary. This is the thing that is like constraining, right? I call this the constraint, or we could say like limiting, right? So let's find the equations for these two things, and we might want to go ahead and give names to stuff. So let's call P the positive rational number, and let's just say N is the negative rational number. All right, use letters that make sense. Okay, so the primary, let's see, what should we call the product? I guess we'll call it big N. So big N is the product. Right, the product between these two is P times little n. Right, so this is my primary equation. You could use different letters if you want to. These are just the letters I'm using. The secondary comes from here. Right? How do I relate the positive rational number to the negative? Well, they tell me the positive number equals exactly 7 greater than the negative. So 7 plus the negative number. Cool. So that's my secondary equation. So now I can plug this into the primary, into this one, and I'm going to get N equals, plug in for P, so we get 7 plus little n times little n. So distribute that in. Big N equals, I'm going to write it in lowering degrees here, so n squared plus 7n. This is what we're trying to minimize. Now we do our extrema business, right? So we're going to take the derivative of big N with respect to little n. Right? So that's going to be 2 little n plus 7. I know I'm using 2 n's here. Just try to keep them straight in your head. Capital N is the product. Little n is the negative rational number. Okay, so I'm going to take this derivative, and for us to have an extrema, this has to equal 0. So that happens at, or when, little n equals negative 7 over 2. So notice how this is a negative rational number, which is what they said it would be. So this is the negative rational number. How do I get P? Well, I just add 7 to that. So P equals 7 plus negative 7 over 2. And this equals, so that's 14 over 2 minus 7 over 2. That's positive 7 over 2. So that's P. Now, they were asking for the final product, right? So we don't have the answer yet. We have to multiply these two. We're looking for big N. So big N, the product would be negative 7 over 2 times 7 over 2. And that equals negative 49 over 4. All right. So that's an interesting one. Just very mathy. It's a very math kind of optimization problem. Not a very real world. I mean, I guess cryptography is a thing, but it's kind of a niche application here. Anyway, let's go to number 2. A rancher wants to construct 2 identical rectangular corrals using 200 feet of fencing. Okay. The rancher decides to build them adjacent to each other. Okay, so that they share fencing on one side. What dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? Largest possible area. This is what we're trying to maximize. This is telling you what your primary equation should be. All right. What is my constraint, my secondary equation? That's the amount of fencing I have. I only have 200 feet of fencing, right? This is like limiting my possibilities here. So now let's get these in equation form, right? And to do that, we might first want to draw a picture. So we're going to have 2 identical rectangular corrals that are side by side, and they share the same fence. So let's sort of draw this here. So here's a rectangular corral, and then I have an identical one right next to it, and they both share that one line of fencing. And we might want to give these some names. So let's call this, I don't know, width. Let's call this length, right? So this is equal to this, equal to this, equal to this. Width, width, width. All right, so that's my corral. Okay, primary equation, area. The area of this thing is equal to what? Total area. So it's the area of both of these rectangular corrals, which it would just be 2 times W times L, or 2L times W, either way, right? Seems straightforward enough. Secondary. So for this, we need to count up all these little pieces of fencing and make sure they're exactly equal to 200, right? They have to be equal to 200. This is what is constraining us here, right? So 200 has to equal, how many L pieces do we have? We have 4 of them. So 4L plus how many W pieces? 3W. Beautiful. Okay, now let's solve for a variable here, and let's plug the secondary into the primary. So I'm going to go ahead and solve for, let's solve for L. Why not? So I'm going to get 200 minus 3W divided by 4 equals L. Okay. Now I'm going to take this. I'm going to take this. Going to substitute it in to the primary. So A equals 2W times 200 minus 3W over 4. Okay, cool. So that means that area equals 400W minus 6W over 4 divided by 4. Is there a better way to simplify this here? This turns into a 2. Yeah, let's simplify it. So we get 100W Yeah, 200 over 2, 100 W minus 3 over 2 W squared. Cool. Now we do our extrema stuff. So over here, we're going to take the derivative of area with respect to the width, W. So this is going to equal 100 minus 3W. And to find the extreme value, right, the maximum possible area, we're going to set this equal to 0, solve for W. And it looks like you get 3W equals 100. That means W equals 100 over 3, or about 33.3 repeating. Cool. And so this is one of the dimensions, right? They're looking for what dimensions should the rancher use, right? So that's one of them. To find the length, well, we would just plug it into the constraint. So take the constraint. 200 has to equal 4L plus 3 times 100 over 3. And it looks like the 3's cancel. Subtract the W to the other side, or sorry, the 100. So you get 100 equals 4 times L. And this means that L equals 25. And of course, we should probably use proper units here. So let me write this a little better. So L equals 25 feet. W equals 100 over 3 feet. There we go. Those are my dimensions. Cool. Cool. Let's keep it going here. Again, feel free to pause, rewind, whatever you need to do. Okay, a company has started selling a new type of smartphone at the price of $140 minus 0.05x, where x is the number of smartphones manufactured per day. The parts for each smartphone cost $80, and the labor and overhead for running the plant costs $7,000 per day. How many smartphones should the company manufacture to sell per day to maximize profit? So last class, I showed you guys an example involving maximizing profit. Remember, profit is revenue minus cost. We use pi for profit, right? Revenue is the number of smartphones times the price, and they actually give us the price right here. This is your price. And so I'm just going to take price, which is this, times quantity. That's my revenue. Minus, I'm going to put in parentheses here, the cost. So it says the parts for each smartphone cost $80. So that's what we call the variable cost, right? So you would take 80 times however many smartphones you make, and that's the cost for making that many smartphones. And then regardless of how many smartphones you make, it always costs $7,000 per day to run the plant. So that's what we call the fixed cost, $7,000. And so now we want to simplify this, right? What we have here is pi as a function of x. So that's function notation there, right? They're not being multiplied. And let's simplify it. So we get 140x minus 0.05x squared minus 80x minus 7,000. Simplifying again, combine some like terms. I'm going to put this one in front. It's the highest power. 140x minus 80x should be 60x and minus 7,000. So this is my profit function as a function of x, the number of smartphones. Okay, now we do our typical extrema stuff. You might have noticed we didn't really, we came up with a primary equation, and then we didn't really do a secondary, but we actually did. We just didn't point it out, right? So the secondary was this the whole time, right? Essentially P equals this stuff. And so what we did was we actually already had plugged it in once we set up the primary equation. Sometimes you can skip steps like that, but I want you guys to, for the most part, write out the primary, write out the secondary. Anyway, let's take the derivative with respect to x. So we could write this as like d pi dx. I'll just put pi prime though. Anyway, so this is negative 0.1 x plus 60, and we're going to set that equal to 0. And it looks like we get x equals 600 smartphones. So that is the amount that we should make to maximize profit. And that's actually what they were looking for. So we actually just got our answer almost immediately, which is great. Okay, cool. Let's keep it going. Oh, you know what? We did a problem very similar to this in class, except I believe we had 0, 2. So the answer is probably going to be a little different now, right? If you remember what the answer was for that one. But it's a very similar thing. So anyway, we did these three. This is where the problems start to become a little harder. All right, so which points on the graph of this, right? So this is what's constraining us, right? We have to be on this curve, right? So this would be where our secondary comes from. In fact, it is this equation. Are closest to the point here. So by closest, we're talking distance. We're talking what is like the minimum distance, right? So this concept here is my primary. And if you remember what we did in class for this one, first of all, you should draw a picture of this. Absolutely. So let's draw a picture. Draw the parabola, right? So here's 4, and then I think at 2, this should be negative 2. So we get a parabola like this. Okay. And we're trying to find the closest point to 0, 3, which maybe isn't that close. Maybe it's somewhere like here. 0, 3. And so the point is, right, if I choose different points on this parabola, they are all different distances, right, from this point, some of them being closer than others. So we want to calculate the distance between 0, 3 and any point in general on the parabola, which all these points, we could just say have coordinates x, y. All right, let's just say that for the time being. All right, every point in the parabola follows that pattern. Sure. Okay. So primary equation. So this would be the distance formula, right? We're going to calculate the distance between 0, 3 and x, y. So that's going to be x minus 0 squared plus y minus 3 squared inside of a square root. That is my primary. My secondary is this guy. Right? So now we can take this, plug it into the primary. So d equals, I'm going to have x squared there. When I plug it in for y, I'm going to get 4 minus x squared minus 3. So we're going to have 4 minus 3 is 1. So we're going to have 1 minus x squared squared. And now we want to simplify this as much as we can, right? So we get x squared plus 1 squared is 1 minus 2x squared plus x to the fourth. I'm just distributing out this binomial here. Okay, simplifying one more time, combine some like terms. Looks like we get x to the fourth minus x squared plus 1. All right, cool. So now take a derivative like we normally do. So we're taking the derivative of d with respect to x. So be careful here. So the derivative you should get, just to save time, should be 4x cubed minus 2x over 2 square root x to the fourth minus x squared plus 1. And yeah, we can factor the top there, it looks like. We can pull out a 2x on the top. So we get 2x squared minus 1 over 2 square root x to the fourth minus x squared plus 1. So that's the derivative of the distance function with respect to x. We want to find when this derivative equals 0. And that seems to be the case for a few places. So what are my critical points here? Well, it's either when this equals 0 or when this equals 0. So the places are x equals 0, and it looks like plus or minus the square root of 1/2, right? Again, just if you don't get that, just set this equal to 0, solve for x, right? Yeah, so that's where I'm getting that from. Now, we don't know if 0, 4 is closer or if the point here is closer. So let's kind of do sort of a candidates test type thing. And let's find the distance for both of these places. So d of 0 equals the square root of 0 to the fourth minus 0 squared plus 1. So that's a distance of 1. D of square root of 1/2 is equal to square root of 1/2 to the fourth minus square root of 1/2 squared plus 1 square rooted. This is going to be, looks like we're going to get 1/4 minus 1/2 plus 1 inside my square root here. So this is going to be 1 minus 1/4. So that's the square root of 3/4, it looks like. So is that right? Yeah, I think that's right. Which is less than 1, right? So, looks like these critical points are my candidates, right? And because it's a parabola, the plus or the minus square root of 1/2, both of those points are the same distance away. So all we got to do now is find out where these, what the y value of these points are, right? So we would do that by taking them and plugging them in to the equation of the parabola. So I'm going to do that for the positive square root value. So this is 4 minus 1/2, which equals 3.5. That's 7/2, right? Yeah, 7/2. So the closest points are square root 1/2, comma, 7/2, and negative square root 1/2, comma, 7/2. Now, if they asked what is that minimal distance, we would give them this number, right? This is the actual minimized distance there. But they're asking for the points, which are these two things. So, anyway. So we did a problem very similar in class, right? Hopefully this makes some sense. Okay, this one, things get a little wonky here, so hang with me. A geometry student wants to draw a rectangle inscribed in the ellipse, x squared plus 4y squared equals 36. What is the area of the largest rectangle that the student can draw? So you definitely need to draw a picture here. All right, so I'm going to draw my ellipse. Now, is it wider or is it taller, right, due to this 4 here? So, like, imagine y is 0. What would x need to be? It would have to be 6. Okay? Imagine x is 0. What does y need to be? Looks like y squared would have to equal 9. And so that means y would have to be 3. So it looks like this is a wide ellipse. Right? We can actually say exactly how wide and how tall it is. So it's going to go all the way out to -6 and +6 here. And then it's going to go up to 3. 1, 2, 3. Okay, something like this. I'm hoping you guys know what an ellipse is. I'm sure you do. Or at least you learned it at some point. All right, there we go. That's good enough. Okay, and the idea is we're taking this ellipse and we're drawing a rectangle inside of it. Okay, so yeah, we're kind of just taking, it's a rectangle that fits in here. Ooh, my ellipse is not good enough to draw this rectangle. Okay, so you kind of want to do a similar trick here that we did with this parabola. So you notice we used a generalized point to represent all points on the parabola. We want to do something similar here, and namely we want to do it sort of at one of the corners of this rectangle. So I'm going to call this x comma y. Now this x comma y is automatically going to help us create our equations, because notice if that's x comma y, then this length is exactly 2x. And then the height would be exactly 2y. Right, because these lengths would be equal because of the symmetry of the ellipse, and so would these lengths. All right, so that's important. Now what we're trying to maximize is the area. Right? That's telling me, hey, my primary equation needs to involve area. Right? So now that I've actually put symbols to some of the quantities here, I can say the area of my rectangle is going to be 2x, the length, times the height, 2y. So that's cool. So the area is 4xy. And my secondary is the ellipse itself. That is my secondary equation. So x comma y has to satisfy this equation. So I've got to go ahead and use the secondary and plug it into the primary, and then we take a derivative from there. So let me go ahead and solve for maybe x. All right, so my secondary, x squared plus 4y squared equals 36. I'm going to solve for x here. And then I'm going to take a square root. So x equals square root of 36 minus 4y squared. Now, technically it's plus or minus, but we're going to basically confine our point to this first quadrant. and that should give us all possible solutions. No matter where this point is, right, in this first quadrant, it's going to help us define every single rectangle we could draw into this ellipse. So we don't have to worry about plus or minus here. Cool. So now, plug this in. Area equals 4 times the square root 36 minus 4y squared times y. I don't know why I'm drawing my y's so differently. Let's maybe write this a little bit better. So 4y square root 36 minus 4y squared. I just moved it over to the front. Okay, now we only have one variable. Let's take a derivative of area with respect to y. So we get, this is a product rule, right? We got one function times another. Don't forget, product rule. So derivative of the first would be 4 times the second. So 36 minus 4y squared plus the derivative of the second. So this is going to be, it looks like, negative 8y over 2 square root 36 minus 4y squared. We're using the chain rule on this, right? That's why the negative 8y comes up top, right? So I just went ahead and put it in the numerator and do the chain rule properly, and you should see why that's the derivative. And then times 4y. Okay, let's try to simplify this thing a little bit. So, yikes. This is not a fun equation to look at. All right, so this is going to stay the same. The 2, I'm going to simplify it with the 4 there. So we're going to get minus 16y over square root 36 minus 4y squared. Okay, let's combine fractions. So I'm going to multiply top and bottom by this square root thing. So this should turn into 4 times 36 minus 4y squared. Yeah, over the square root of 36 minus 4y squared minus this thing. This is where you got to really lock in and just keep following the equations here. Okay. So, what are we left with? Let's distribute the 4. Let's combine some like terms if we see them. I don't see any. So really it looks like we're just going to have minus 16y squared minus 16y plus, let's see, 4 times 36, 160 minus 16 is 144. So it looks like plus 144 over square root 36 minus 4y squared. Cool. And what's extra nice is because y can only be as big as 3, we really would only get one undefined critical point, which is at 3. But we know that if that were true, then our rectangle would literally just be zero area. All right, so we actually don't need to worry about the critical point at y equals 3. So really all we need to do is factor the top and solve for when this equals 0, right? So if I do that, let's keep the work going up here. I'm going to factor out a 4, a negative 4, I guess. So negative 4. So we get 4y squared minus 4y plus 30. 36, yes, 36. Oh, and you know what? I can factor out another 4. Let me go ahead and do that, actually. So we're going to factor out 16. 16. Yeah, I should do that. So you get y squared minus y. And I believe you get 9. So this would be this would be plus y plus minus, so minus 9 over square root of 36 minus 4y squared. That should equal 0. Oh man. Okay, well, look at this. Quadratic, not factorable. Boo. Okay, that's okay. We can figure this out. We've got to use quadratic formula, right? So this is going to equal 0 when y equals, so negative b plus or minus radical b squared minus 4 times 1 times negative 9, all divided by 2 times 1. So we get negative 1 plus or minus radical 1 plus 36, so that's square root of 37, divided by 2. All right. And, of course, we would take the positive version here because we're only looking at this first quadrant, right? We're only considering that. So our y equals 1, negative 1 plus square root of 37 over 2. And we're trying to find the area. So if that's my y, my x, we would have to plug that into the ellipse formula to get the x, and then we would have to multiply the two numbers to get the area. All right, so let's go ahead and do it. Can't leave this problem unfinished, so I'm going to take my y value, plug it into my ellipse formula to get the x value. So I'll make a little barrier here. X squared plus 4 times y squared equals 36. 36. Okay, so this will be x squared. It'll be plus 4 times. Let me do it like this. Negative 1 plus square root of 37 squared over 4 equals 36. Right, now you can see those 4's cancel. That's super nice. Right, so we get x squared plus, we're going to get 1 minus 2 root 37 plus 37 equals 36. So x squared minus 2 root 37 plus 38 equals 36. So x squared equals, let's get all that junk over. So it looks like we're going to get negative 2 minus 2 root 37. Oh, this should be a plus. Plus, yes. So negative 2 plus 2 root 37. Cool. So I got my y value, my x value. So the area would be, the area equals 4 times x times y. So it would be equal to 4 times my x value, 37, times my y value, which is -1 plus square root of 37 over 2. There we go. I know that doesn't look like a really nice, clean answer, but that is the answer according to what we found. All right, last one. Let's finish strong. All right, so which point on the graph of y equals square root of x is closest to the point 3, 0? So again, draw the situation. So y equals square root of x. And then we have, 1, 2, 3. Here's my point, 3, 0. And which point is closest? So we've seen a problem very similar to this, right? So there's lots of different points that are all different distances. And so a point in general on this curve, we could just say is x, y. And the thing we're optimizing is closeness, or like the distance, right? We're trying to get that distance as small as we can. So our primary equation is going to be the distance formula, right? I'll use d. So d for distance. D equals, in this case, we're going to have, looks like we could do maybe x minus 3 squared plus y minus 0 squared. And then what is my secondary? Well, you could probably guess. It's the equation of the curve itself, right? That is our secondary. So let's plug the secondary into the primary. So d equals x minus 3 squared plus, now y minus 0, that's going to be square root of x squared. Cool. So d equals, we're going to get x squared minus 6x plus 9, and then plus an x in a square root. Add some like terms. We get x squared minus 5x plus 9. Cool. Now, next step, we have our function we're trying to optimize. Take a derivative. Right, so we're taking the derivative of dd, with respect to x. And so, hopefully you guys recognize how to do this kind of derivative by now, right? You're going to have a chain rule effect, so this is the derivative of the inside that shows up in the numerator. And then we're going to have over 2 square root of whatever's on in the inside originally. Cool. So the question is, when does this equal 0? Well, it seems to equal 0, right? Our critical point seems to happen at x equals 5 over 2. And it looks like there's no other critical points. Yeah. Looks like there are no other critical points unless, just to be sure, right, we should probably check. If this can equal 0, then we have an undefined derivative. So maybe let's just check that the solutions here are imaginary. Right, so quadratic formula time. Negative b plus or minus radical b squared, so it's 25, minus 4 times 1 times 9. Oh, yeah. So look at that discriminant. Right, that's going to be a negative number. Square root of a negative is imaginary. So this is my one and only critical point. Awesome. So what is the y value? Well, y equals square root of 5 over 2. So my final answer, wow, this one was a lot quicker than the last one. 5 over 2, comma, square root of 5 over 2. Excellent. So we're going to go ahead and end it right there. So thank you guys for watching. I know there was a lot of stuff, especially that ellipse problem was kind of crazy, but this is optimization. This is the kind of stuff, you know, it has a lot of applications to all sorts of situations. So take care.